Welcome to the Deep Dive. You know, today we're really getting into some deep science stuff.
Oh, yeah.
With the oxygen dissociation curve,
ODC.
or ODC.
For short.
I love it when we can shorten things.
Yeah.
But this is something that I think a lot of people find kind of intimidating.
Absolutely.
And it's so important for our audience.
Yes.
The medical lab professionals.
Yeah, it's a fundamental concept for understanding, blood gases.
Exactly.
And how oxygen is transported throughout the body.
So we have some great research articles.
Yes, we do.
And your incredible notes.
Thank you.
I'm so excited to dive in.
I think what's really interesting is that people often forget that the ODC is not just some, theoretical graph.
Yeah.
It's a visual representation of, our very breath.
Oh, wow.
It shows how our red blood cells,
Right.
those tiny little couriers, are carrying oxygen.
Hemoglobin's the star.
Hemoglobin is the star.
That little protein inside.
Yes.
The red blood cells.
It's an oxygen magnet.
That's a good way to put it.
And its ability to bind and release oxygen is what makes life possible.
Right.
And the ODC illustrates that relationship.
Okay.
So the curve plots the percentage of hemoglobin saturated with oxygen against the partial pressure of oxygen.
Now there's a term, PO2.
Yes.
So PO2, partial pressure of oxygen.
That's right.
Sounds kind of complicated.
It's basically the pressure exerted by oxygen
Okay.
in a mixture of gases, like in our blood.
Okay.
Because air is not pure oxygen.
Right.
It's a mixture.
And why is this pressure so important?
Imagine a crowded room
Okay.
where everyone's vying for space.
Okay.
That's high partial pressure.
I see.
So oxygen, just like people, wants
Right.
to move to where there's less people.
So less crowded.
From high PO2 to low PO2.
So that's diffusion.
That's diffusion.
I remember that
Yeah.
from high school chemistry.
Exactly.
So in our lungs, where oxygen is plentiful,
Yes.
high PO2, it moves into our blood
Yes.
where there's lower PO2. Okay.
And then as blood circulates to the tissues where oxygen is being consumed,
Right. Yeah.
the PO2 drops even further.
Yeah.
And that's where hemoglobin
Yeah.
adjusts its grip on oxygen.
Now, this is something I was looking at before we started recording.
Yeah.
The ODC isn't a straight line.
No, it's not.
It's that S-shaped,
It's a sigmoid curve.
that sigmoid curve. What's up with that?
That reflects the cooperative binding of oxygen
Interesting.
to hemoglobin.
Okay.
So at low PO2, hemoglobin is reluctant to bind oxygen.
Mm-hmm.
It's being cautious.
Okay.
But once one oxygen molecule binds,
Yeah.
it's like, okay, come on in, guys.
Oh, so it changes.
It changes the structure
Interesting.
and makes it easier for others to bind.
Okay.
So it's like a party.
Oh, like that analogy.
Once a few people show up, it's much more attractive for others to join in.
That makes sense.
And that's what gives the ODC its steep slope in the middle.
Okay.
And then as the PO2 increases further, the curve plateaus.
So it kind of levels off.
It levels off. Yeah.
Okay.
It means that even if there's more oxygen available, hemoglobin is maxed out.
Okay. Like a sponge.
Like a full sponge.
It's full of water. Can't take anymore.
Yeah.
So the ODC is showing us how hemoglobin's affinity
Yes.
for oxygen changes.
It changes based on the PO2.
So high affinity in the lungs
Yeah.
to grab it,
Grab all the oxygen.
and then lower in the tissues
Yeah, lower affinity in the tissues.
to release it.
Exactly where it's needed.
Oh, this is so cool.
Here's where it gets even more fascinating.
Oh, I love it when you say that.
2,3-DPG.
Oh, yeah, that rings a bell.
Remember that molecule?
Vaguely.
We talked about it. I
Yeah.
think it was something about
Red blood cells
red blood cells.
and fine-tuning oxygen
Yes.
delivery.
It's produced by red blood cells during glycolysis.
Okay.
And it modulates the ODC.
Wait, so it can actually change
Yes.
how hemoglobin interacts with oxygen?
Yeah, it binds to hemoglobin
Okay.
and makes it less greedy for oxygen.
Less greedy.
Less greedy.
Okay.
So it causes the entire ODC to shift to the right.
Okay, so if it shifts to the right,
Yes,
that means that hemoglobin's grip on oxygen loosens, even at higher PO2 levels.
precisely.
Okay.
This rightward shift is crucial in situations where your body needs more oxygen.
Like exercise,
Like exercise.
or like if you're at high altitude,
high altitude, yeah.
less oxygen.
Exactly.
So in those cases,
Yeah,
having a right-shifted ODC is a good thing
it's a good thing.
because it helps ensure that your tissues
Yes.
get the oxygen, even when things are
Yeah.
a little oxygen challenged.
Exactly. It's a brilliant adaptation.
It's amazing how the body does that.
And this brings us to another critical aspect of the ODC, its ability to shift
Ah.
in response to various conditions.
Okay.
Physiological conditions
Yeah.
in the body. Yeah, it's like the ODC is this finely tuned instrument adjusting to the body's needs.
Right.
And beyond 2,3-DPG, there are other factors.
Oh, yeah. In our notes, I'm seeing
Yes.
CO2, pH, even temperature.
Temperature
Can shift that ODC.
can make it dance.
Make it dance. Okay, so
Yeah.
let's break those down because these are all things that,
Yeah.
our listeners are measuring
Exactly.
in the lab
All the time.
all the time.
So let's start with CO2.
Okay.
Carbon dioxide.
Okay.
Which is a byproduct of cellular metabolism.
Right.
So as CO2 levels rise, the blood becomes more acidic.
Okay.
This increased acidity is represented by a lower pH.
I see.
And that encourages hemoglobin to release oxygen.
Okay, so more CO2.
More CO2.
Lower pH.
Lower pH.
ODC shifts to the right.
Shifts to the right.
More oxygen to the tissues.
Exactly.
Which makes sense because those active tissues are producing a lot of CO2.
Exactly.
Right, and this relationship between the CO2, the
Yes.
pH, and the ODC. I mean, we see this when we exercise.
Oh, absolutely. That's a classic example.
Yeah, because our muscles are working harder.
Yeah, they're burning more fuel.
Right.
Producing more CO2.
More CO2 and lactic acid.
Lactic acid, yep.
And so that causes a rightward shift of the ODC.
To deliver more oxygen to those muscles.
That's so cool.
Yeah, it's amazing how the body just knows.
Knows what to do.
What to do.
Okay, so what about temperature?
Temperature.
How does that play into all of this?
Well, think about what happens when you exercise.
Okay.
Your muscles heat up.
They do.
And just like increased CO2 and acidity, higher temperature also promotes oxygen release.
So heat also shifts the ODC.
He also shifts it to the right.
To the right.
To the right.
Okay.
So we've got these three players.
Yeah. CO2, pH,
temperature,
all working together to influence the ODC and ultimately oxygen delivery.
Oxygen delivery, that's the goal.
I'm also seeing here a mention of P50. What is that all about?
That's a crucial parameter that helps us quantify these shifts.
Okay.
So it represents the partial pressure of oxygen at which hemoglobin is 50% saturated.
So it's like the midpoint.
It's like the midpoint of the curve.
Of that curve.
Yes.
Okay.
And the beauty of P50 is that it gives us a single value that reflects the overall affinity of hemoglobin for oxygen.
Oh, okay.
So a higher P50 indicates a lower affinity.
Okay.
Meaning hemoglobin releases oxygen more easily.
Okay.
While a lower P50 means a higher affinity. So it holds on tighter.
Okay. So for example, in our exercising athlete, their P50 would be higher.
It would be higher.
Because of that rightward shift.
Exactly.
Because their body needs to make sure that oxygen is getting to those muscles.
Absolutely.
Okay, so understanding these P50 variations is really valuable for our listeners when they're interpreting those.
Yeah.
Blood gas results.
Blood gas results, that's right.
Okay, now we need to talk about acid-base disorders.
Oh, yeah.
Because I know that these can really throw a wrench in the whole oxygen delivery system.
Absolutely.
Yeah.
These disorders really highlight the play between the ODC, the pH, and oxygen delivery.
Right.
So let's start with metabolic acidosis.
Okay.
Which is a condition where there's an excess of acid in the body.
Okay, so in metabolic acidosis, the pH drops.
The pH drops.
And we know acidity shifts the ODC to the right. So does that mean that more oxygen is getting to the tissues?
Yes, but it's not quite as simple as that.
Okay.
While a rightward ODC shift does promote oxygen unloading, we need to understand the cause of the acidosis.
Okay.
In metabolic acidosis, that increased oxygen delivery is a compensatory mechanism.
Okay, so it's the body trying to...
It's the body's way of trying to counteract that low pH.
Right, because in this case,
Yeah.
the increased oxygen delivery
Yes.
isn't necessarily a good thing.
It's not a good thing.
It's a sign that something's wrong.
It's a sign that the body is in distress.
Okay, so what about metabolic alkalosis? Where the pH is higher?
Yeah, pH is higher than normal.
Okay.
So in that case, we see the opposite effect. The higher pH or decreased acidity shifts the ODC to the left.
To the left.
To the left, making hemoglobin hold on to oxygen tighter.
So in alkalosis, we might see a decrease.
Yeah, we might see a decrease in oxygen delivery.
Interesting.
And this can have significant clinical implications.
Right.
Especially if it's severe or prolonged.
Right. So we've covered the metabolic side.
Yeah.
What about respiratory acidosis and alkalosis?
Respiratory acidosis, it is where you have an inability to eliminate CO2 effectively.
Right.
Usually due to lung disease or impaired breathing.
So this CO2 retention leads to
Increased acidity.
Just like in metabolic acidosis.
So the end result is the same.
The end result is the same.
Right, word shift.
And again, it's a compensatory mechanism.
Right. The body's trying
to fix the problem.
Okay, and I'm assuming then that respiratory alkalosis,
yes,
the opposite, it would shift it to the left.
It would shift it to the left because you have lower CO2 levels,
right,
leading to a higher pH,
okay,
which favors oxygen binding.
So the takeaway here
is
that these acid-base disorders
yes,
can have a big impact.
Huge impact.
On the ODC?
Yes.
And oxygen delivery.
Oxygen delivery to tissues.
To the tissues.
Yeah.
And that's what's important.
And for you, our listeners,
yeah,
understanding these relationships is crucial.
Yeah.
For interpreting blood gas results.
And, providing valuable insights for patient care.
Absolutely. So we've covered a lot of ground here.
We have.
From the basics of the ODC all the way to acid-based disorders.
Absolutely.
But how does this all play out in real-world scenarios?
Yeah. Let's put our ODC expertise to the test.
I like it. All right, scenario number 1.
Okay.
We have a patient suspected carbon monoxide poisoning.
Okay.
Their skin is cherry red.
Classic sign.
Complaining of a headache.
Yep.
And their blood gas results show a high oxygen saturation.
Okay.
But they're clearly not getting enough oxygen.
Yeah, this is where understanding the ODC can really help.
Okay.
Because carbon monoxide binds to hemoglobin with a much stronger affinity
than oxygen.
So
even though the hemoglobin is saturated, it's saturated with the wrong thing.
It's saturated with the wrong molecule.
It's like having a delivery truck that's full of the wrong packages.
Yeah, exactly. It's a great analogy.
So the ODC itself might not look that different.
Right.
But the problem is what's bound to the hemoglobin.
Exactly. You got to consider the whole picture.
Okay.
The patient's symptoms.
Right.
The potential presence of other molecules.
Like carbon monoxide.
Unlike carbon monoxide, exactly.
Okay, case number 2.
Okay.
We've got a premature infant.
Okay.
Respiratory distress syndrome.
Oh, yeah.
Their lungs aren't fully developed.
Yeah. They're struggling to breathe.
How does the ODC?
Yeah, so premature infants often have a deficiency of surfactant, which helps keep the tiny air sacs in the lungs open.
Right.
So this makes breathing very difficult.
Okay.
And can lead to low oxygen levels in the blood.
So we're dealing with a low PO2.
Low PO2.
So does that mean the ODC shifts to the left?
Not necessarily the ODC itself. Might not shift dramatically. Yeah. It's more about the reduced driving force for oxygen to move from the lungs to the blood.
Because that PO2 is low in the lungs.
Lower PO2 in the lungs
makes it harder.
Harder for hemoglobin to get saturated.
So that's why these infants might need supplemental oxygen.
Exactly, or even mechanical ventilation.
To help them breathe.
Okay. So it's all about optimizing that pressure gradient.
Got it.
For oxygen uptake.
Okay. Final case.
Right.
Patient with chronic anemia.
Okay.
They've had low hemoglobin levels.
Yep.
They're always tired.
Classic anemia.
So
anemia means fewer red blood cells.
Fewer red blood cells.
Less hemoglobin.
Less hemoglobin to carry the oxygen.
Exactly.
But does the ODC change?
The shape of the ODC stays the same.
Okay.
The issue is the reduced oxygen carrying capacity.
Because there's just not enough hemoglobin.
Not enough hemoglobin.
It's like having fewer delivery trucks. Even if those trucks are working fine, there's just not enough of them to get those packages delivered.
To meet the demand.
So even though the hemoglobin might be working fine, there's just not enough there. So this helps us understand their blood gas results and what we can do to treat them.
Exactly.
Like iron supplements.
Iron supplements.
Blood transfusions.
Blood transfusions.
Wow, these cases have really helped me understand how the ODC works.
It's amazing how this simple curve plays such a crucial role.
In so many different things.
In so many different conditions.
Yeah, it's amazing.
It really is.
It's a testament to the body.
To how brilliant our bodies are.
Yeah, and for our listeners, understand the ODC is like...
It's like having a secret decoder ring.
Oh, I love it.
For oxygen transport.
Yeah, and it helps you provide those insights for patient care.
Patient care, that's the goal.
Well said to our listeners.
Yes.
Keep those lab coats crisp, those minds curious, and never underestimate the power of the oxygen dissociation curve.
The ODC.
Until next time, this has been The Deep Dive.